Okay, hello everyone. Thank you all so much for coming, and thanks to Jacob for inviting me to talk at the seminar. It's a great pleasure. So as you can see today, I'm going to be talking about Penrose and his criticisms of string theory. Actually, this talk has been particularly long in the making. It's 20 years since Penrose's monumental book, The Road to Reality. And like many teenagers, soon after it came out, I picked up a copy for myself and read some of it. And some of the stuff that I read was about Penrose on string theory. And I immediately noticed, he's super critical of string theory. That's very interesting, given how popular it seems to be amongst other theoretical physicists. At the time, though, I didn't really understand much about what Penrose was saying, and it's been on my mind several times in the intervening 2 decades to look at this carefully and to do justice to Penrose's arguments against string theory and try to make sense of them. That really only came to fruition last summer when I was looking at this properly with my excellent student Maciej Kratki, who I think / hope is in the audience today. And the product of our discussions was a paper which is now on the Phil Sci archive. So the talk is going to adhere quite closely to the content of that paper, and you can look at it if you're interested. Okay, so let's jump in then. So in The Road to Reality, but also in his later book, Faith, Fashion, and Fantasy, Roger Penrose criticises string theory and its practitioners from a variety of angles. And today I want to assess Penrose's critical discussions of string theory, focusing in particular upon those which invoke the notion of functional freedom, which is an idea which Penrose discusses at some length in these books and which I'm going to introduce for you as well. So the plan for the talk is this. I'm first of all going to talk about functional freedom and tell you what Penrose means by that. We're then going to think about functional freedom and its relation to notions of theoretical equivalence. Penrose also talks about that a little bit, but I think that there's room to kind of disambiguate exactly what he has in mind. We're then going to talk about string theory. I'll just introduce to you the relevant aspects of string theory. And with all of that stuff on the table in roughly the first half of the talk, we'll then look at Penrose's arguments against string theory. In the second half of the talk, we're going to classify them into 4 distinct arguments, those to do with counting functional freedom, those to do with exciting the extra degrees of freedom in string theory, those to do with the supposed classical instability of those degrees of freedom, and finally, arguments to do with initial data. Great. So hopefully that all sounds okay. So let's start off with the notion of functional freedom. So I need to say just a little bit about field theories before we get there. So typically, when you're constructing a field theory, you begin by considering a differentiable manifold M, which can be thought of as a background on which physical events are unfolding. Those physical events pertain to fields which assign some value to each point or attribute to each point in the manifold. If you label those fields by phi, then you could think of them as functions from the manifold to this space F, which is a differentiable manifold of field values. And clearly that would be different for like scalar fields or vector fields or whatever it is. So then kinematically possible models of a generic field theory could be specified as tuples M and then a bunch of fields on the manifold. This is philosophers' jargon, which is by now fairly entrenched. And then the dynamically possible models of a theory would be the subset of the kinematically possible models picked out by appropriate dynamics. For example, the Einstein equations or Maxwell's equations or whatever. This might be a bit more delicate when you get to quantum theories, and you might have to talk about dynamical possibilities as being picked out by Parthic integrals or something like that. But thankfully, we won't need to worry about that in this talk. A field theory thus consists of a specification of the kinematical possibilities together with some dynamics which allow one to pick out the dynamical possibilities from amongst the kinematical possibilities. Okay, so Penrose is also considering things in this kind of framework. And in his discussions of functional freedom in the context of field theories, he starts off by providing plausibility arguments to the effect that the cardinality of the set of kinematical possibilities will be the same, Aleph1, regardless of the precise dimensions of M or of these field value spaces F. I'm just going to grant that that's the case, follow Penrose in this regard. Nevertheless, we might want to have a way of comparing the number of degrees of freedom of one field theory versus another one. Kind of intuitively, a vector field theory has more degrees of freedom than a scalar field theory. So how could we make sense of that? So asking this question, Penrose initially proceeds via a kind of discretization heuristic. He approximates M and these spaces F by discrete manifolds consisting of only a finite number of points. And then he's going to take the continuum limit eventually. So one might try then to recover the original manifolds from this picture by taking the limit, like I said. So as an example, consider this field theory T, whose kinematical possibilities are given by R3 and then a three-dimensional vector field on R3. And then consider a three-dimensional cubic lattice of n cubed points on which there live a discretized three vector field, which was formerly V. So I've replaced this guy and this guy with their, or the field space associated with this guy with their discretized equivalents. And note, so in other words, suppose that each of these n3 points is assigned a vector whose components may take one of k values, and note that both n and k are in the natural numbers here. Then a simple combinatorial argument would yield k to the 3n cubed as the total number of possible field configurations on the lattice, since each of the n cubed points can be assigned one of k cubed possible vectors. Hopefully that makes sense. So generalizing, if I had C independent components over a D-dimensional lattice, I would get the functional freedom as being k to the Cn to the D. Now, you might think that in the continuum limit where k and n go to infinity, this guy's just going to become infinite, and I'm not going to be able to compare the number of degrees of freedom of theories anymore. But that's precisely where Penrose resists. And he says, let's just nevertheless push on with this kind of notation and use it as a way of comparing the number of degrees of freedom of various different field theories. So in this particular case, when I take k to infinity and n to infinity, I'm going to end up writing down something like infinity to the C, infinity to the D. And he uses notation like this to compare the functional freedom of this theory versus the functional freedom of that theory. This kind of notation is exactly what he means by functional freedom, which ultimately is a way of comparing sizes, which in some sense is meant to cut finer than the orders of infinity that we're familiar with. Okay, so take that to be a notion of functional freedom, which is really just to do with the size of the spaces which I'm using to define my field theory. I haven't said anything about dynamics up to this point. So suppose now that our theory does have non-trivial dynamics. Intuitively, the dynamical equation should decrease the functional freedom of the theory, since the fields are now subject to constraints coming from those dynamical equations. So to capture that distinction, you could talk about the kinematical functional freedom of a theory, which is just the functional freedom needed to specify the spaces of the objects under consideration, like we were doing on the previous slides, versus the dynamical functional freedom, which is functional freedom which takes into account the dynamical content of the theory. And the dynamical functional freedom will be less than the kinematical functional freedom. So as an example of this, and actually this is just from Penrose as well, the kinematical possibilities of vacuum electromagnetism in the F field formulation you would take to be M eta F, where M is a smooth manifold and eta is the Minkowski metric on M, and F is the Faraday tensor. For the purposes of obtaining dynamical functional freedom, it's convenient to represent this theory in terms of the electric and magnetic components which are bundled up in that Faraday tensor F. Then the kinematical functional freedom of the theory would be infinity to the 6, infinity to the 4, because I've got 6 electric and magnetic field components on 4-dimensional space-time. The dynamical functional freedom is going to be computed in the following way. So dynamics, of course, is implemented via the Maxwell equations. Penrose thinks about this in terms of an initial value formulation. So consider some 3-dimensional space-like hypersurface in the manifold. Once the values of E and B are specified on this hypersurface sigma, you can use the two dynamical Maxwell's equations to evolve the fields to the future of sigma. And that would decrease the functional freedom from the original infinity to the 6, infinity to the 4 to infinity to the 6, infinity cubed, since I'm doing stuff on the 3-dimensional hypersurface here. But then I also need to impose the constraint Maxwell's equations, which is going to further decrease the functional freedom. And there are two such constraint equations. So Penrose argues that eventually the functional freedom, when they incorporate dynamics, is going to be trimmed down to infinity to the 4, infinity cubed, which hopefully makes sense to people. And And note this is, of course, smaller than the kinematical functional freedom of the theory. So this is the kind of presentation that you see in this Penrose article and also in the two books. There are some reasonable open questions here. So how should gauge degrees of freedom be incorporated into this framework? Should they be taken to contribute to the dynamical functional freedom of a theory, or should they be removed via a gauge fixing condition? And what about other things like non-physical ghost fields, etc.? I think what's become clear to me is that Penrose, partly as a result of very charitable email discussions which Penrose had with us after we put our paper on the archive, is that Penrose does intend to remove all of the gauge degrees of freedom when he's computing dynamical functional freedom. So that will kind of go to some way to answering these questions. But just to say, it's not maximally clear what to do with these kinds of things if you're just reading the books. So I'll come back to all of this gauge fixing business in a minute, but now just to say something about the relationship between functional freedom and cardinality. So Penrose insists that functional freedom does capture a sense of magnitude, but resists its identification with Cantor's theory of infinite cardinals. So here's a quote from Faith, Fashion, and Fantasy where Penrose talks about this. He says, "The first point that I should make is that these infinite numbers do not refer to the ordinary Cantor sense of cardinality that describes the sizes of general infinite sets. Cantor's theory of cardinal infinities is really concerned just with sets, which are not thought of as being structured as some kind of continuous space. For our purposes here, we do not need to take into account continuity or smoothness aspects of the spaces that we're concerned with. For example, points of the one-dimensional line R are just as numerous in Cantor's sense as the points of the two-dimensional plane. However, when we think of these points on the real line or the real plane, respectively, as organized into continuous line or a continuous plane, the latter must indeed be thought of as a much larger entity in the limit when the finite n-element set R becomes continuous R." So he's clearly asserting that there is a difference between the functional freedom notion of size of R2 versus R, even though in terms of Cantor's notion of infinite cardinals, they're the same. Does this make sense? Well, it's not super clear. So here are some kind of skeptical thoughts. If Penrose maintains that the functional freedom is not a cardinal number and yet believes that two functional freedoms may be meaningfully compared in size, it's tempting to accuse him of inconsistency, because the standard linguistic practice in mathematics understands terms like larger and smaller and more or less in terms of Cantor's cardinals or in terms of measure theory. Engaging with this linguistic practice by making comparisons of functional freedom would seem to commit Penrose to functional freedom just being Cantor's cardinals, which is what he denies. So if we're to make sense of what he's doing, maybe one way to go would be to see him as engaging in what in the philosophy of language is known as conceptual engineering. So inviting us to revise these concepts. There's a whole book about this by Capellan, which Mache and I talk about in our article, but I won't talk about it more here. But note that this is pretty radical, and it's also not super clear that we've been giving an argument here. We've just been presented with the assertion that this is bigger than this, but one might wish to see more than that. So we're a little bit skeptical about whether this really makes sense. But anyway, that is Penrose's notion of functional freedom. And hopefully at least the rough idea is clear to people. So let's just take it for now and then see what Penrose does with it. So in all of these sources, so that 2002 paper, also these two books, Penrose alludes to functional freedom as being related to notions of theoretical equivalence. I started off being somewhat skeptical about whether there was anything here, but actually, as a result of conversations with Enrique Gomes this morning, I'm a bit less skeptical now. So unfortunately, the section has become marginally more dialectically complicated than it was 24 hours ago when I was thinking about what to say in this talk, but so be it. So let's see what Penrose says about the relationship between functional freedom and criteria of theoretical equivalence. So one important quote is this quote from Faith, Fashion, and Fantasy. So Penrose says that a theory cannot be equivalent to another theory on which the initial space has a different number d of dimensions, since the freedom in the d space theory will be bigger than that of the other theory. And it's tempting to extract from this a statement about the relationship between equivalence of theories and dynamical functional freedom. You might think that Penrose is saying that theories T1 and T2 are equivalent only if they have the same dynamical functional freedom. That notion of equivalence, though, can be disambiguated in a bunch of ways. So the first thing that you might read Penrose as saying, which ultimately I think is the most plausible, is this. So theories T1 and T2 are physically equivalent. They represent the same physical goings on, only if they have the same amount of dynamical functional freedom. So agreeing on dynamical functional freedom is a necessary condition for two theories being physically equivalent. You would worry about that if you thought that mismatches, it would be sufficient to observe that a mismatch in dynamical functional freedom between two theories doesn't imply that they're physically inequivalent. And if you just populated one theory with extra gauge degrees of freedom, it would seem like this is not satisfied, but you might still want to regard the theories as being physically equivalent. I actually don't think that's super fair to Penrose, though, because, as I mentioned earlier, I think really it's clear to him that you should be subtracting the gauge degrees of freedom when computing dynamical functional freedom. So that kind of just like randomly populate one theory with extra unphysical degrees of freedom wouldn't be something that he is particularly moved by. Okay, good. So this does seem to have a kind of degree of plausibility if my computation of the dynamical functional freedom of two theories proceeds by purging both of those theories of gauge degrees of freedom. There are also separately, though, possible worries about this principle, because there might seem to be cases where I have two theories which I would want to regard as being physically equivalent, even accommodating gauge, and yet their dynamical functional freedom is different. So I'm going to present the example. I'm now less moved by this example, and this is where the conversation with Enrique comes in. So I'll present the example, and then I'll tell you what's going on. So let us consider the dynamical functional freedom of electromagnetism, but not formulated in terms of the Faraday tensor, but formulated in terms of a four-vector potential. So kinematical possibilities of that theory would be tuples m, eta, and a, where a is a one form with the usual gauge redundancy. So the kinematical functional freedom of this theory would be infinity to the 4, because I'm dealing with a four-vector on four-dimensional space-time. Dynamics are picked out by this dynamical Maxwell equation. And then let's proceed like Penrose did for the Faraday tensor formulation of electromagnetism when we're thinking about the dynamical functional freedom of this theory. So consider a three-dimensional space-like hypersurface sigma. Since that equation is second order in time, you need to specify both A and its derivatives in order to fix the evolution to the future of sigma. This amounts to 8 components not subject to any constraints. So then I'd have infinity to the 8 infinity cubed. Then subtracting the gauge fixing conditions, which is the prescription which you find in Penrose's writings on this, you would seem to arrive at infinity to the 7 infinity cubed, which is not, granting that the notion of functional freedom makes sense to begin with, the same as the dynamical functional freedom of the Faraday tensor formulation of the theory, which, recall, was infinity to the 4 infinity cubed. So here it looks like I have a problem case for EC1, because I have two theories which I would want to regard as being physically equivalent, which don't seem to have the same dynamical functional freedom when computed in this way. Now, I think actually this problem case is not as worrying as it might first appear. Although in this slide, we've been using the prescription for computing dynamical functional freedom, which is given to us by Penrose in the books. In fact, there are more sophisticated ways of counting the number of degrees of freedom of a theory, which I think would help Penrose out. And to be fair and to be clear, I'm 100% sure that Penrose knows about these, and I'm pretty sure that he wouldn't have talked about them in the book, because this is meant to be a kind of semi-popular book, and all of this gets a bit delicate. So this is what Enrique pointed me to. So For example, if you look at Henno and Teitelbaum's book from 1994, they give a much more sophisticated prescription for counting the number of degrees of freedom of a theory, which involves counting the number of first and second class constraints in that theory formulated in the constrained Hamiltonian formalism and subtracting them in the appropriate way. And actually, if you apply this prescription to the case of vector potential based electromagnetism, I think actually, I won't go through it here, but we could discuss it in the Q&A if you wanted to, that the number of degrees of freedom of vector potential based electromagnetism actually does end up agreeing with the number of degrees of freedom of Faraday tensor based electromagnetism. So ultimately, I'm more open than I initially was about EC1, this principle that two theories are physically equivalent only if they share the same dynamical functional freedom. I'm more open to this as being like an acceptable principle than I was, but I think that it's worth being clear that first of all, you have to take into account the gauge degrees of freedom of these two theories, which is not something which is totally clear in the books. And also, I think that you should use something like this way of counting degrees of freedom from Henno and Teitelbaum. Then we seem to be able to share something like, to save something like that principle. Okay. That's not the only way that you could read that equivalence condition, though, and other places in Penrose's writing seem to invite a slightly different reading. So another thing that you could say is that two theories are weakly empirically equivalent, so they agree on some empirical data, but not all of it, only if they share the same dynamical functional freedom. Or you could have this principle EC3, which says that two theories are strongly empirically equivalent. They agree on all possible empirical data, only if they share the same dynamical functional freedom. EC2 is, I think, quite evidently not a good principle. You could have two theories, for example, say general relativity and Newtonian gravitation theory. They make the same empirical predictions if you're ignoring certain kinds of observations to do with Mercury and so on. If you think about the rest of the solar system, say, there's no reason to think that those theories have the same dynamical functional freedom. So this doesn't look like a good principle. Those theories are weakly and empirically equivalent in a certain domain, but they don't have the same dynamical functional freedom. If you turn to EC3, this maybe also seems a bit problematic. Why should strong empirical equivalence, agreement on all possible empirical data, require the same numbers of the same amount of dynamical functional freedom? Couldn't I have two theories, perhaps adjudicated to be physically inequivalent by the standards of EC1, which have different amounts of dynamical functional freedom, which nevertheless make the same empirical predictions? I'm going to come back to EC3 in a little bit when we talk about what Penrose has to say about holography. So all of that discussion is a little bit delicate, but just to say that Penrose does talk about the relationship between theoretical equivalence and dynamical functional freedom. I think that this could be cashed out in three different ways, with some tweaks that theories T1 and T2 are physically equivalent only if they agree on dynamical functional freedom, i.e. EC1 seems not so bad a principle. EC2 seems obviously bad, I would say, and EC3 seems at least unmotivated. Cool. So I will return to those principles in a little bit when we get on to Penrose's arguments against string theory. But now we can catch our breath and move away from functional freedom and think about string theory. So I'm very sure that many people in the audience will already be familiar with the physics that I'm about to describe, but just for those of you who aren't, let me go through a little bit about the relevant basics of string theory, which will be important for Penrose's arguments against string theory. So as I think we probably all know, string theory is supposed to be not only a theory of quantum gravity, but a theory of everything. It begins with an ontology in one way or another, which consists of quantized strings in some space-time background. And the thought is that by studying those strings and various quantum states of those strings, I can derive not only the Einstein field equations of general relativity, possibly with corrections, but also, ideally, familiar particle physics phenomenology. That's at least the aspiration of string theory. typically when you open a string theory textbook, what you'll see right at the start is what's known as the Nambu-Goto action. So this is the action describing a classical relativistic string in a Minkowski spacetime background. What you would want to do is to quantize this action to get quantized strings and then see what I can do with them. This turns out to be a little bit problematic because of the square root in the action here. It makes quantization very, very difficult. But thankfully, people have tricks up their sleeves. Just to say right now, these sigma here is denoting the string world sheet. So note that this isn't the same as my space-like hypersurface from before. And these x's describe the embedding of the world sheet in the Minkowski spacetime eta. Good. And these sigmas are the coordinates on the world sheet. So like I said, quantization of this thing turns out to be very, very difficult due to the square roots appearing in the action. But thankfully, string theorists have a way to get around this. What they use instead is what's known as the Polyakov action, which I've written on the slides here. Here I have an extra variable, this auxiliary world sheet metric h. This could be removed by varying this action and getting the equation for motion for h and then plugging it back in. So it's kind of a standard first course in string theory exercise to get the Nambu-Goto action back out of the Polyakov action. But the Polyakov action turned out to be much easier to quantize than the Nambu-Goto action. Something which is going to be very important for us is that the Polyakov action, in addition to being reparameterization and Poincare invariant, is also invariant under conformal rescalings of the world sheet metric. Like I said, that's going to be important, especially for deriving something like the Einstein field equations from this string theoretic setup. So there are lots of different ways to quantize the Polyakov action. In my first course on string theory, I had 24 lectures on string theory, and I'm pretty sure that like 20 of them were about quantizing the Polyakov action. Thankfully, we don't actually need to do it in any detail here. Let me just describe to you one of the ways in which you could proceed, which would be to view the Polyakov action as describing a two-dimensional conformal field theory on the world sheet, and then you perform a path integral over the world sheet fields, including both the x's and the world sheet metric h, as well as extra ghost fields, which you have to introduce to make things work. Yeah, that's basically what you do. Once you've quantized the string, here's in extreme brevity how you end up saying something about the behavior of gravity on the space-time background, or recovering something like the Einstein equations on the space-time background. I'll just give you the kind of point-by-point prescription about what happens, but none of these are very straightforward. So you start off by quantizing the string. You then define ladder operators to study its excited states. In particular, you study the first excited states of the string, which for the bosonic string are three different things. I've got this symmetric spin-2 field F here, which is suggestively christened the graviton. I've got a two-form B, and I've got a scalar field phi, which is known as the dilaton. These are the kind of, these are the first excited states of the bosonic string. And then you make, in my opinion, highly non-trivial move, which, by the way, is discussed and studied very nicely in Huggett and Wuttrich's forthcoming book, Out of Nowhere, in the chapter on string theory. Once I've got the first excited states of this string, I then consider coherent states of strings in space-time. So imagine a space-time region populated by strings which are all in this first excited state, and then I consider some limit or some state of the string in which stringy effects can be ignored and quantum effects can be ignored. And then via some often kind of hand-waving in a couple of paragraphs, I get to another field on space-time, which looks like this, F. This is highly non-trivial, let me be clear, and I think worthy of study and being cashed out properly. But this is what you'll see if you look at string theory textbooks like Green, Schwartz, and Witten, the move from first excited states of a string to coherent classical string states on the manifold. Once I've got that, so I've got my background space-time manifold populated not only by my original Minkowski metric, but also by my coherent states of strings, which would be some classical field F and some classical field B and some classical field phi. I then look at the world sheet invariance of the string. And that world sheet invariance of the string actually, if you compute beta functions for the world sheet conformal field theory, imposes constraints on those background fields. And in particular, it imposes that those background fields must be dynamical and obey to first order the Einstein field equations. So this is a pretty cool calculation, actually, and kind of looks like magic. But hopefully the if not the details, which I haven't even presented to you, but the general idea here is okay. So I've got a quantized string, study its excited states, move from the excited states of such a string to coherent states on the spacetime manifold, and then use worldsheet invariance of the string to impose dynamical constraints on how those background spacetime manifold fields must be related to each other. That's a derivation of the Einstein equations in string theory, which to my knowledge was first done in the mid-80s, and it was presented very nicely by, for example, Huggett and Vistorini in their 2015 article on this, as well as more recently in this book by Huggett and Wittrick, which I mentioned. So the moral so far would be that perturbative string theory could be viewed as a two-dimensional quantum field theory, which upon past integral quantization yields consistency conditions on the background fields in which the strings propagate, which can be understood to be dynamical equations for those background fields. The strings are kind of doing double work. They're both giving you those non-trivial background fields, and they're giving you constraints on how those background fields have to be related to each other. If I were to think about these things in a kind of KPM-type language, then you might write down the kinematical possibilities of perturbative string theory as being picked out by the string worldsheet and the fields on the string worldsheet and the ghost fields on the string worldsheet. And from all of that, I seem to be able to derive facts about, yeah, like I said, how fields on spacetime are behaving. It makes some sense, but if I'm starting like this, it's not a particularly four-dimensional spatiotemporal picture. Really, all of the work is happening on the string worldsheet. And you might want a way of understanding string theory, which is more analogous to how we're familiar with doing quantum field theory. One option here, which was originally constructed, I think, at least in the 1980s. Yeah, probably in the well, probably not earlier than the 1980s, which has come and gone, but is maybe undergoing some of a resurgence now, is the program of string field theory. So the idea here is that you have a four-dimensional spacetime manifold. You take that to be the kind of fundamental thing. And I define, in analogy with quantum fields, string fields at every spacetime point in the manifold, and then I study the excited states at each spacetime point. That's a very kind of geometrically straightforward way of going, which seems like a natural generalization of quantum field theory. For a long time, it turned out to be not to be popular because it's technically challenging to think in this way. But like I say, it's still an ongoing research program, and it has some kind of pictorial advantages over the perturbative presentation, which I was discussing up to now, in terms of you can think about the world really as being consisting of fields on a space-time manifold, just as before, if I think in this way. If anyone's interested, there's a very nice recent textbook on string field theory by Urban, which I would recommend. So just to say a little bit more about string field theory, and this is the last slide, and then we can get to Penrose's objections to string theory in general. The fundamental objects of string field theory are open and closed string fields, which you could call phi and psi. So open string field means it's a string field where the excited states of the string are going to correspond to oscillations of some open string, and the closed string field, same kind of thing, but where the excited states at each spacetime point are going to correspond to different oscillations of closed strings. You can imagine, or you to envisage those fields as living on a background spacetime manifold M. So you could take kinematical possibilities to be M, phi, psi, like this. That simple appearance belies a lot of complexity. In perturbative string theory, so the formulation that I was presenting you with before, excitations of the open string give rise to a tachyon and a massless gauge boson, and identifying an infinitely many more massive particles of higher spin labeled by a discrete quantum number alpha and continuous momentum k. In string field theory, all of this is packaged up into the excited states of the string fields at every point. So my string field kind of looks like this if I were to think about expanding it in terms of those states. Cool. Okie doke. So that's enough about string theory. Hopefully that was tolerably clear, but if people have questions, we can talk about it. in the Q&A, or if there's anything basic, you can ask me now. Let's now combine our discussion of functional freedom and our discussion of string theory to see and assess what Penrose has to say against string theory. So we'll go through the 4 kinds of arguments that he presents us with. And let's start off with the arguments to do with counting the amount of functional freedom. There seem in these sources to be 3 main functional freedom counting sub-arguments against string theory, which Maciej and I call the classical physics argument and the heterotic string argument and the ADS-CFT argument. So let's go through each of these in turn. So in Faith, Fashion, and Fantasy, Penrose observes the discrepancy in the amount of dynamical functional freedom of worldsheet perturbative string theory, so that first formulation of string theory, which I was giving you on the one hand, which he tries to compute, and on the other hand, ordinary physics. So he computes the functional freedom of worldsheet perturbative string theory to be infinity A to the infinity 1 versus infinity B to the infinity cubed. I can't quite remember what A and B are, but you can see that these are going to be different, and concludes that this is problematic. The amount of functional freedom of worldsheet perturbative string theory is not matching the amount of functional freedom of what he calls ordinary physics. He also observes that the full functional freedom of worldsheet string theory might not be easily ascertainable. Note that these are 2 really distinct worries. The first is kind of a metaphysical fact about the number of degrees of freedom of one theory versus another, whereas the second seems more epistemological in nature. On that epistemological worry, I think we're unmoved. We don't quite see why this should count as an objection to string theory. It might point to a limitation of the theorist, but it's not obvious that not being able to straightforwardly ascertain the amount of functional freedom of a theory is a damning problem with said theory. On the metaphysical worry, the worry that the amount of functional freedom of string theory isn't the same as the amount of functional freedom of ordinary physics, I don't think we're super convinced either. Why would you expect that to be the case? And really, what does that even mean? If the amount of functional freedom of string theory is different from the amount of functional freedom of electromagnetism or whatever else is that we're looking at when we mean ordinary physics, I'm lacking an argument as to why that's problematic. One thing which you could say, which is not so much to do with functional freedom, but which is really more to do with an issue of being able to picture what's going on, is something along the lines of what I was saying before. If I'm treating my kind of 2-dimensional worldsheet conformal field theory as being the fundamental thing, it's not super obvious how I'm to visualize emerging from just that, a theory of extended space-time. And if I think about the string oscillating and the constraints on the background fields which are imposed by the conformal invariance of the string worldsheet fields, at best I seem to be able to get constraints on the background fields like where the string lives, but it's not obvious I can go from that to a picture of kind of normal 4-dimensional space-time ontology, or at least that's often elided in discussions of perturbative string theory. So I think in some sense, maybe Penrose is in the right vicinity here, but it's more an issue of not really being able to visualize exactly what's going on in perturbative string theory, rather than an issue with the number of degrees of freedom or the amount of functional freedom per se. That's what I would say. I think when it comes to his second of these 3 arguments, something similar is going on actually. So the second of the 3 arguments is what we call the heterotic string argument. So just to remind you, everything which I said in my presentation of string theory in that previous section was to do with what's known as bosonic string theory. So I wasn't introducing fermionic fields, I wasn't introducing supersymmetry or anything like that. But if I want to recover the phenomenology of the standard model of particle physics with both bosons and fermions, I need to introduce supersymmetry somewhere. I need to have both bosons and fermions. There are 5 different ways to do this, 5 at least on the face of it, distinct versions of perturbative superstring theory. There are 2 different heterotic string theories, and actually these seem to be the most effective for recovering something close to, albeit perhaps not exactly the same as 4-dimensional space-time particle phenomenology that we're familiar with. But the heterotic strings are a bit strange because they seem, on the face of it, to have left moving modes and right moving modes, which at least mathematically appear to be moving in different number of space-time dimensions. The left moving modes seem to look like they're moving in 26 space-time dimensions, whereas the right moving modes seem to look like they're moving in 10 space-time dimensions or vice versa. Mathematically, this makes sense and is consistent, but it's a bit puzzling how to visualize what's going on. So here's what Penrose has to say about it. The strange feature about heterotic string theory is that it appears to behave simultaneously as a theory in 26 space-time dimensions and in 10 space-time dimensions, the latter with accompanying supersymmetry, depending upon whether we're concerned with left-moving or right-moving excitations of the string. This dimensional conflict would seem to cause us problems if we're to try to work out the functional freedom involved. I find it very difficult to form a consistent picture of what's going on here, and I've never seen these geometrical issues properly discussed. So there are really two things here, right? The first is how to compute the functional freedom of the heterotic string, and the second, how to visualize what's going on. It's kind of mirroring what was going on in the previous objection. So you might worry about how to compare the functional freedom of perturbative string theory without ordinary physics, and you might also worry about how to visualize what's going on. So what can we say about this? Well, let's think about heterotic string field theory. I don't need to read the whole of this quote, but the consensus from people who work on the heterotic string seems to be that you actually should treat it as living in 10-dimensional space-time, even though some of the modes look like they're living in 26-dimensional space-time. Actually, that's not the way to interpret what's going on. So if that's right, then would this be a consistent geometrical picture for Penrose, and would it help with computing the amount of functional freedom? I would like to think that the lack of ambiguity about what the space-time dimension really is, at least to some degree, ameliorates the concerns which Penrose is raising here. I would also say that the real concern in here is about visualizing what's going on geometrically rather than about counting functional freedom, or at least I think it's worth teasing those things apart. Okay, so the third counting degrees of freedom argument is something which looks at the ADS-CFT correspondence, which is a holographic duality between 10-dimensional space-time living in the bulk and a 4-dimensional conformal field theory living on the boundary of that space-time. So I've got string theory living on the inside and something more like a normal quantum field theory living on the boundary. And of course, this is super famous and is very, very striking that these two theories, which seem to be kind of physically very distinct, agree on correlation functions and so on. But Penrose is concerned about it. He sees a problem in the mismatch of the dimensionality of the ADS theory set in 10-dimensional space-time and the conformal field theory living on the boundary. He sees this as problematic, and he takes it to indicate that the theories cannot be equivalent, even empirically equivalent. But this seems to us to be too fast. First, because it's an open question whether the theories have the same amount of dynamic or functional freedom. Remember that Penrose's settled view, I think rightly, is that you have to purge the theories of gauge degrees of freedom. And it's not obvious that just the space-time dimension is going to be the right way of ascertaining what the dynamic or functional freedom of those two theories is. And second of all, even if you grant that there's a mismatch of dynamical functional freedom, why should that imply empirical equivalence? Sorry, why should that imply empirical inequivalence? In his writings, he says that these two theories must be empirically different because they have different amounts of dynamical functional freedom. But why does that follow? So that's essentially asserting our equivalence condition 3, but I don't see any justification for that. And it's not obvious that two theories could have different numbers of physical degrees of freedom, but nevertheless have the same empirical content, agree on what Van Fraassen would call empirical substructures in their models. Okay, so none of those arguments look super convincing. Let's go on to the second argument against string theory, which Penrose raises, which is to do with exciting extra degrees of freedom. So here's how this one goes. This involves excitation of the extra degrees of string theory, extra degrees of freedom in string theory associated with its supposedly extra functional freedom, which in turn is to do with its like excess number of space-time dimensions. So To say a bit more about this, I first of all need to say a little bit about compactification in string theory. So in order to recover four-dimensional space-time phenomenology in a 10-dimensional superstring theory or a 26-dimensional bosonic string theory, theorists have studied models in which the additional dimensions are compactified into a manifold of small size. So if I wrap up the extra dimensions so small that I can't see them, that would be one stab at recovering something like a four-dimensional space-time phenomenology. So for the superstring, which is set in 10 space-time dimensions, that compact manifold is typically taken to be a Calabi-Yau, threefold for various reasons to do with, amongst other things, preservation of supersymmetry. So that string theoretic space-time takes the form of M cross X, where M is this Calabi-Yau threefold manifold. There are lots of different Calabi-Yaus that you could use here. And that leads to a proliferation of string theory particle models. Depending upon how I compactify the extra dimensions, I'll get different particle phenomenology. And this has sometimes been called the landscape problem of string theory, which I won't discuss more, but I recently wrote something about with Baptiste Leban, so those who care can look at this. I'll present you with a simple example of compactification before getting on to the worry from Penrose. So consider the product manifold M cross S1, where M is familiar four-dimensional Minkowski spacetime and S1 is a circle of small radius rho. Then you could write down the Klein-Gordon equation on this spacetime like this, where sigma denotes a coordinate along the S1 compactified dimension, and this is the usual Box-Stellenbertian operator on M. Then if I expand this field in terms of the modes associated with this compactified dimension S1, I can write the Klein-Gordon equation like this. And you'll notice that if this compactified dimension has small radius, then this becomes a large effective mass. And then the reasoning is that if this were super small, this would become such a massive mass that I wouldn't detect it in particle experiments. That's the kind of reasoning that people give about how ultimately you can ignore modes on the compactified dimension if they're wrapped up tightly enough. Okay, so something similar, albeit not exactly the same, because we're doing compactification on Calabi-Yaus, is going on in superstring theory. But Penrose does not like this compactification picture. And he worries about the energy which it would take to, as he puts it, excite these extra space-time dimensions. So here's a quote from Penrose, and then we'll assess it. So I'll read it out and then we'll assess it. So are the positive energy Planck scale modes of vibration of the 6 extra dimensions immune from excitation? Although the Planck energy is indeed very large when compared with normal particle physics energies, it's still not that big an energy, being comparable with the energy released in the explosion of about 1 ton of TNT. There is, of course, enormously more energy than this available in the known universe. For example, the energy received from the sun by the Earth in 1 second is some 10 to the 8 times larger. On energy terms alone, this would be far more than sufficient to excite the compact space for the entire universe. So what's going on with this passage? So crucial in this passage seems to be the notion of exciting a degree of freedom. What Penrose means by this isn't, especially in the context of string theory, maximally clear. Maybe one way of understanding what he means is to think in terms of string field theory. So I've got my string fields on spacetime, and their various components could become excited. They could go into excited states, just like ordinary quantum fields. But this doesn't seem to square completely with Penrose's worry. If excitations of the string field around the background coherent state were to occur, they would surely need to be facilitated by localized means rather than by what Penrose calls delocalized TNT explosions happening over a wide space-time region. But Penrose thinks that those explosions happening over a wide space-time region could excite the extra dimensions of string theory. It's just not obvious why this is so. And also it seems to be in conflict with how we would think about excitation in quantum field theory. In quantum field theory is localized energy, i.e. high energy density, which is relevant. One could ask, why does the situation have to be different in string theory? I think it's just unclear to Mache and I why we should worry about excitation of the string theoretic degrees of freedom, whatever that ultimately means, on the basis of delocalized low energy density type situations. Moreover, when Penrose says that the entire universe would be excited, thereby affecting physics in, for example, the Andromeda galaxy very far away, this would seem to presuppose that all copies of that compactified space-time dimension over M would get excited in the same way. But that's, I think, a puzzling geometrical picture. If I'm thinking about M cross X as a product space, any excitation of X would surely happen locally in M cross X. So at any particular point in the manifold, one excites the X space near that point or at that point, but that wouldn't translate to exciting the X space associated with the space-time points, which are super far away. So a lot of this worry about exciting the extra dimensions, the extra degrees of freedom, and in terms of how you would do that via delocalized energy, and in terms of that happening across the entire universe, I think just seem, puzzling to us. Okay, so the third argument is this. So this has to do with singularity theorems proved by Hawking and Penrose, and Penrose in particular appeals to a theorem which he proved with Hawking in 1970. And the worry is about the instability of the extra degrees of freedom in string theory. So the assumption behind Penrose's reasoning seems to be that the background fields in string theory are to an excellent approximation described by the Einstein equations derived from the vanishing of the beta functions, coming in turn from the Worldsheet conformal invariants like I was talking about before. Note that that's only an approximation. Actually, the true dynamics involve extra additional terms to the Einstein field equations. Penrose just ignores those, but let's just set that aside. He just uses just the Einstein field equations. So what's the worry? Consider a compactified string theoretic spacetime M cross X, where X is our small Calabi-Yau and M is Minkowski spacetime. Since M you could decompose as R cubed cross R, you could regroup the product terms and define Z is equal to R cross X. And then you can study the perturbations of an initial value surface in Z. The theorem of Hawking and Penrose states that the evolution will result in a singularity provided that the dimension of Z is greater than or equal to 3, and Z contains a compact n-1 dimensional hypersurface without closed time-like curves, and second condition, that the strong energy condition is satisfied, which is this. Penrose's conclusion is the following. What the singularity theorem appears to be telling us is that so long as the perturbations of the extra dimensions can be treated classically, as indeed appears to be a reasonable thing to do, and as a clear conclusion of our earlier considerations, then we must expect violent instability in the 6 extra spacetime dimensions, in which they crumple up and approach a singular state. Whatever the extra dimensions might crumple to, the observed physics is not likely to be other than drastically affected. This is hardly a comfortable picture of the 10-dimensional spacetime that string theorists have been proposing for our universe. So what to make of this? Here are some things that you could say. So Penrose seems to believe that that strong energy condition is certainly satisfied in string theory because it follows from the vacuum Einstein equations, which Penrose assumes to hold on this manifold M cross X. But recall that the full dynamics of the background fields, like I said, isn't just given by the Einstein field equations, but it's given by the Einstein field equations plus corrections. And so it's not obvious that the strong energy condition should actually be regarded as being something which obtains, or at least it's something which is needed to be shown. And I'll come back to that in just a second. Even granting Penrose that the low order approximation of the full dynamics is just the vacuum Einstein field equations, that's also not obviously pertinent to string theory, where it's not the vacuum equations, which would be the accurate model for those string theoretic backgrounds, because I derive non-vacuum versions of the Einstein field equations plus corrections. When it comes to energy conditions in string theory, like I said, you would actually need to also show that this thing is satisfied. There's been some work in this vicinity, but I don't think it's yet sufficient to help Penrose. So these authors in 2015 derived the geometric null energy condition in perturbative string theory, but that's weaker than the strong energy condition, which Penrose needs, so it doesn't obviously help. Either we need to show that the strong energy condition, which is also something which is satisfied in perturbative string theory, which hasn't been done yet, or Penrose would have to use a different singularity theorem to illustrate his point. Cool. So there seem to be a lot of places where you would push back against this argument as well. So the fourth argument isn't something which I'll spend a great deal of time on, but I will present it to you. So this is an argument, a worry about the amount of data that you have to specify on an initial surface. if I'm using those Einstein field equations plus corrections, which you get from perturbative string theory. In this case, Penrose says this: more serious to my mind is the fact that the full requirement involving all orders in the string constant, just the Reggie slope parameter, is actually an infinite system of differential equations of unbounded differential order. Accordingly, the data that would be needed on the initial 9 surface would involve derivatives of all orders in the field quantities. The number of parameters per point needed on the 9 surface would then be infinite, so we would get functional freedom of infinity to the m, infinity to the 9. For any positive integer m, this would seem to make the problem of excessive functional freedom even worse than before. I'm not aware of any serious discussion of the mathematical form that this requirement would take and of what kind of initial data might be appropriate for it. So the basic worry here is that I need loads of functional freedom to specify the initial data if I'm doing an initial value problem in the string theoretic framework, because the salient background field equations of motion are not just the Einstein equations, but the Einstein equations plus corrections, which involve arbitrarily high order derivatives, all of which you would need to specify to have a well-posed initial value problem. I don't think that that infinity of terms and their unbounded order is inherently problematic, because the Cauchy problem could still be well-defined and the system solutions exist. All of this is a bit delicate. You might also ask why you're interested in doing these kinds of problems in string theory, but even if you set that aside, there's just more to work out here. So this might be okay as long as convergence is secured, but we know that beta functions generally don't converge, so it's not obvious that this is going to work. I think ultimately just more needs to be said when investigating this problem. Okay, so there's a lot going on. I kind of rattled through all of this, but let me just summarize to you what I've been saying, and then hopefully we can have some decent discussions about it. So I started off presenting you with Penrose's notion of functional freedom. This is meant to be distinct from our usual understanding of orders of infinity. It's not obvious that it actually gives us that. The relationship between functional freedom and equivalence is most plausibly understood as a relationship between physical equivalence of theories and agreeing on dynamical functional freedom, if you take into account gauge degrees of freedom and use a more sophisticated way of counting degrees of freedom than Penrose at least explicitly offers. Then I presented to you string field theory and perturbative string theory, and then I went through these arguments. So we had arguments about counting functional freedom. So Penrose was worried about the apparent discrepancy between the amount of functional freedom of perturbative string theory and classical physics, or the amount of just computing what the amount of functional freedom of the heterotic string is, or about comparing the amount of functional freedom of bulk theories versus their associated boundary theories. In all of these cases, we were broadly unmoved, and insofar as there was a real issue here, it seemed to be an issue about visualizing what's going on rather than the amount of functional freedom of the theories. We also had worries about exciting the extra degrees of freedom, but the big confusion here seems to be the idea that you could excite string theoretic degrees of freedom with delocalized low energy density, and I frankly simply don't really understand what Penrose means there. I'd be interested to hear people's thoughts. The third problem was a worry about classical instability, but Penrose invoked a singularity theorem, which might not obviously apply in string theory, and also the conditions for said theorem are not obviously satisfied. And fourth, there was a worry about specifying initial data to solve the string theoretic equations in all of their full glory, but it's just not obvious whether this should be taken to be a damning problem. Okay, so let me summarize, and then yes, like I said, looking forward to discussing with all of you. So Penrose raises many arguments against string theory, often relying on the notion of functional freedom. Today, I've questioned whether this notion of functional freedom is well defined. I've discussed the relevance of functional freedom for notions of theoretical equivalence. And in many, but not all, of Penrose's arguments, it seems like they're unsuccessful. Cool. Thank you all for listening.
All right, welcome back, everybody, from the break. We're going to begin the discussion Q&A. I see a hand from Nick. Nick, please go ahead. And very nice to see you, Nick.
When you can see me. Yeah, hi. Thanks, James. And we can talk some more on Thursday, probably. So this is great, and I'm really glad someone sort of tackled those counting arguments from Penrose, because always found them kind of mysterious. So that was great. So this was just a sort of small point. I mean, I have a general question, which would be I'd be very interested to hear more about what Penrose said in response to the paper. But the actual question / comment was just, am I right in remembering what he says there? It's the dimensions that he's most kind of worried about because they make the biggest sort of difference. So if you have like the number of the dimension of the field kind of, he's less worried about that, and he might say that they could be equivalent if it didn't agree in the sort of lowest order exponent, but when you get to the higher exponents, that's what he's really worried about. Is that about right? And does that make any difference to anything?
It might explain why he's particularly worried about things like ADS CFT, but I guess my view is that it's too premature to say to draw anything too much from that observation that the dynamics are different. The jury's out about what's gauge in these two theories and what's not. And that would ultimately affect whether, assuming that we're purging theories of their gauge degrees of freedom when counting functional freedom, whether they have the same dynamical functional freedom or not. I would also say that even if we do take into account the fact that the dimensions are different, and so that's going to give wildly different amounts of dynamical functional freedom, the move to saying that the theories must therefore be empirically inequivalent seems to me to be unmotivated. So I think that you're completely right that these are the kinds of differences, i.e. differences in a number of space-time dimensions, where Penrose is most concerned. But I'm still not sure that that's kind of warrants all of the conclusions which he goes on to draw.
Good. Yeah, no, thanks. That sounds right to me. I was just sort of thinking of slightly weaker versions of the ECs that you were given that sort of allowed some variation in the number of in the functional freedom, but yeah.
Fair. Yeah, maybe it would be difficult to have anything like that in the case where the space-time dimensions are radically different.
Yeah. Okay, thank you. And thanks again. That was great.
Yeah, looking forward to seeing you later this week.
Thanks, Nick. I don't see any other hands currently up. I have a number of questions, if it's okay.
There's also a question in the chat, Jacob.
I'm sorry, I missed that. I'm so sorry, Celeste. My apologies. I'd be interested in hearing more discussion of the landscape problem and this question of 26 versus 10 dimensions, if there's time. Yeah, please go ahead, James, if you would like to reply to that.
Yeah, I'll say something super quick, super brief about the landscape problem. So the landscape problem is the general worry that lots of Calabi-Yau compactifications are possible and allowed in string theory. I guess whether you regard this as being a problem depends upon what you think the kind of aims of science are. So if you're following Van Fraassen and think the aims of science are to construct a theory which is empirically adequate, then you might not be so perturbed about the fact that there are loads of different Calabi-Yau compactifications, as long as there's at least one which is such that the resulting model recovers the empirical facts. That would seem to be sufficient to have a good theory of quantum gravity, which describes our world. So if you have that kind of more empiricist outlook, I think you would be just not as concerned by the landscape problem. The people who are concerned by the landscape problem are people who tend to have stricter criteria for what a theory of physics, and in particular a theory of everything or theory of quantum gravity, should do. So one of the main proponents of the landscape problem is Lee Smolin. I think he has an article on this in Foundations of Physics, and he has stricter criteria. He says that in a final theory of physics, everything should be explained. And if I look at the string theory landscape with loads of different Calabi-Yau compactifications, there doesn't seem to be any explanation for why it was this one rather than that one. And so by those standards, there seems to be a problem. So you can see what might drive some people to think this is a problem and others not. But I guess I'm on the more empiricist side and more sanguine about some things not being explained as long as we get the empirical facts right. On 26 versus 10, I'm not exactly, so no one is saying that those two dimensions are equal, but it's just like some bits of how the string is behaving look like the string is situated in 26 dimensions, and other bits look like they're living in 10 space-time dimensions. And that seems puzzling from the point of view of visualizing what's going on. But our investigations into what string theorists say about the heterotic string suggest that really you should think about the string living in 10 dimensions. I guess there's still a question about like what exactly the heterotic string is doing in those dimensions. I don't know exactly the answer to that question, but at least string theorists don't seem as worried about the kinds of things that Penrose is worried about in the context of the heterotic string.
Thanks so much. I don't see any other hands, so maybe I can ask some of my questions. I spent quite a lot of time on string theory. It was a major part of my doctoral dissertation. So I've been thinking about actually some of these same questions for a long time, and that's why I'm particularly thrilled that we're having this discussion. Okay, so I have a whole list of questions here. Let me start with, I think in some ways, to me, the elephant in the room, which is that Penrose's sort of classification of field theoretic models and his approach to counting functional freedoms seems very classical, right? He's talking about like classical looking field degrees of freedom on space-time manifolds and counting components. This discussion about dynamical equations that we're imposing, dynamically possible models and counting dynamical functional freedoms seems to involve imposing classical equations of motion, classical field equations, classical constraints. But, the connection between string theory and GR is supposed to be not a classical connection, but a quantum mechanical connection. You've got to go through path integral quantization of the string. And then you're supposed to see the emergence of general relativity in this very indirect way that has to go through a quantum a version of the story, and this is phrased in the language of path integrals. It can be rephrased in a Hilbert space language, right? Famously, you can split the path integral open and see what's going on level with Hilbert spaces. And once you go from something that looks like a KPM, kinematical possible model, phrased in very distinctly classical language, or a set of KPMs, or the set of solutions to a KPM. Once you go from that to thinking in terms of some Hilbert space description, then I kind of lose the thread of Penrose's classification and counting. So maybe you can help me understand a little bit, what is the argument that Penrose's argument survives, being pushed through quantization?
I think this is an absolutely fabulous and crucial question. And as far as I'm aware in his writings, he doesn't talk about it. I hope that's right. At least as far as I'm aware, he doesn't talk about this question at all. So it seems like there are exactly the kinds of things which you should address. Like, first of all, how am I to understand quantum fields on space-time? If I'm thinking about like operator valued fields or something, then things are gonna be different. And cashing out exactly how many, or figuring out exactly how much functional freedom there is going to be a delicate project, and he doesn't say anything about it. And then his idea of dynamics is trimming down the number of the amount of functional freedom. So in the equivalence, so right here the dialectic was something like this. So he offers a particular way, but then it seems to give the kind of unpalatable verdict that the amount of dynamical functional freedom of F field electromagnetism isn't the same as the amount of dynamical functional freedom of A field electromagnetism, which is why Enrique suggested to me earlier today that he should really be using the stuff from Hello and Teitelbaum. But even this is phrased in the constrained Hamiltonian formalism as in the context of classical theories. And so it's not obvious that it's applicable to any quantized theory. And I'm not really sure how to use path integrals, or however I'm thinking about the dynamics of some quantum field theory as trimming down the amount of functional freedom in the same way, which is all really just to repeat your questions. I don't really know the answers, and it seems...
Let me make this even more concrete. So there's a paper that Joe Polchinski wrote, unfortunately close to the end of his all too short life, all about dualities. It's a beautiful, beautiful paper that I think presents a really compelling picture about how many people in string theory think about dualities. I highly recommend it. It's extremely readable, very interesting, and very philosophically rich. So the way he talks about a duality in the context of a quantum theory, like he gives a definition of duality. I don't know that one would regard this as a totally general definition of duality. Certainly, when you read the philosophical literature on dualities, it doesn't exactly coincide with Polchinski's formulation. But the way Polchinski thinks about dualities in the context of quantum mechanical theories is, and he's very precise about this. He says a duality is a single quantum theory in the sense that there's some particular Hilbert space formulation that has multiple qualitatively different classical limits. Again, I think you could argue that's a somewhat narrow understanding of what a duality can be, but I think it's telling. I think it's relevant to this particular discussion. So let me give you a concrete example of this. Suppose I have a particle in one dimension, one spatial dimension, classical particle in one spatial dimension, subject to a simple harmonic oscillator potential. So basically a 1D simple harmonic oscillator classically.
Yep.
Now suppose instead I have a discrete classical system. It's got a discrete configuration space. The configuration space is equivalent to the set of non-negative integers. And the dynamics is super simple. Basically, every time you go from the nth configuration to the n plus first configuration, you add a constant discrete amount of energy. There's a discrete energy step. So these are qualitatively very different looking systems. If you try to count functional freedoms in these two classical systems, I think, well, one of them has, it's basically 1 degree of freedom on an infinite line, so you get one particular counting of degrees of freedom. The other one has a countably infinite, 1 degree of freedom with a countably infinite number of values. I guess you could think of it as one-dimensional if you want, although maybe I don't know whether dimension even makes sense in that fully discrete case. Neither is supposed to be a discretization of the other. They're both supposed to be exact theories. But of course, we all know that they're both distinct limits of a single quantum model. The quantum harmonic oscillator contains, the position basis, whose natural classical limit would look like the classical 1 degree of freedom on the line. But of course, if we switch to the energy eigenbasis, well, that there is a sense in which that has a semi-classical description where we forbid superpositions, and then that looks like the second model. So these are two classical models that share the same Hilbert space description. They look qualitatively very different. I don't think there's any meaningful sense in which you could count their functional freedoms and say they're the same. Yep. And I think basically what string theorists are trying to say is that there's some string or M theory, that's some quantum theory with some Hilbert space, or maybe some generalization of a Hilbert space, and it has various limits, some limits that look semi-classical like strings. Most string theorists don't think that the perturbative string sector, encompasses the entire quantum theory. They regard the perturbative string sector as only telling you about certain limiting regimes of what they think is a much larger theoretical construct. And then of course, another limit is a limit that looks like classical GR, or there are various other limits, right? This is sort of the point of all the string dualities, that you have all these different qualitative looking descriptions, and that there could be many different classical limits. So again, I just think that we have some rather concrete examples of when you go from classical descriptions to quantum descriptions, you get a real breakdown in naive counting of functional freedoms, even in very elementary examples like the harmonic oscillator. So I'm just wondering, is this a thing that, and I apologize, I haven't read Penrose's work on this. I didn't read the references that you cited in your talk. Are you aware at all of him addressing these subtleties? And what are your thoughts about them? I'm very curious to know what you think.
My confidence is like 95% that he does not talk about these things. And it seems like they are important. So I'm taking there to be two main issues here. First of all, just like articulating what the functional freedom or dynamical functional freedom of quantum theory is. And second of all, the kind of maybe problematic interaction of what Penrose says about functional freedom and equivalence with these kind of this Polchinski understanding of dualities. Because if I'm using Polchinski's understanding of dualities, I would seem to have theories which are dual but not equivalent according to Penrose, which just doesn't seem like a super happy place to be. So I take both of those points, and I feel that these are both legitimate worries. Yes, I would love to know his response. If he's still willing to talk to me, I might ask him.
I'm just putting a link to the archive paper with the Polchinski review because it is just so interesting, and I think it was in fact written for a special issue of Studies in History and Philosophy of Modern Physics, which is remarkable. Not usually where he would have published. Okay, so I see some more hands. I actually have more questions too, but I'm gonna defer to the audience. So Brian, please go ahead. And then after Brian, I'll go to Noel because because Nick already asked, I think, right? Brian, go ahead, please.
Thank you, James, for your great talk. Unfortunately, I missed a little bit, so I'm sorry if this was covered. I sense that you felt satisfied with cardinality as the classification for infinities. I was wondering if either Penrose or you and your student have taken a look at at the work of people like Vieri Benshi, Mauro Donasso, and a little closer to philosophy, Leon Horston and Sylvia Windmakers. They seem to traffic reasonably successfully and consistently in infinitesimals and infinities and so on. So maybe, maybe there are strategies for making more rigorous sense of what Penrose is up to. And I'm certainly not asserting that's the case, but some of the intuitions and general flavor you would want of having something finer than cardinality without contradicting yourself seems to be achieved by these people. So yeah, I guess that's the question.
That's super helpful. I'm not aware of this literature at all. If you would be willing to send me the links, I would really love to read it. I guess I would like to know whether their way of cutting finer than cardinality does everything that Penrose would want. That would be one question. One of the things which came out of the email correspondence with Penrose is that he also thinks that his notion of functional freedom can be set on rigorous mathematical footing. And actually he says this in a footnote in Road to Reality, and I think another footnote in Faith, Fashion and Fantasy as well. But I wasn't convinced about the maths that he's pointing to there. He talks about using jet bundles to do this, and I just don't really see how that's going to help us. That doesn't seem to be the right set of resources. But then Penrose is much smarter than me, so I don't know. But yeah, I think that what you're pointing to could really be something which could help him out.
Thank you. I'll send it.
Nick has a finger on the discussion. Nick, do you want to just say it out loud? I know you put it in the chat.
Oh, sure. That was just, yeah. So you didn't have to come back to me. People could just see. I mean, I was just going to say, because I really liked that point about dualities there. I think that's a very nice thing to say here. But I was just going to note, Penrose doesn't think that you can have quantum superpositions of the gravitational field. And I don't know if that's sort of in the background. He might bring that up to justify here. I mean, as you noted, and as James said, to get to the Einstein field equations, it's going to have to be quantum enough to allow the beta function analysis. But somehow, I guess he would think that superpositions would be prevented, even in this case.
That seems like a different set of reasons to object, though, and to deploy this. I mean,
well, I took Jacob's point to be, yeah, but the gravity is going to be quantum, so the degrees, the degrees of the functional freedom counting is going to have to be quantum. But one thing he might say is, no, it's still classical. There is a reason, at least, to keep the gravitational field classical here and not go to quantum for this particular case.
So just a note, we started a couple minutes late because of technical problems, so I'm actually going to go a few minutes over the hour. I want to make sure that Noel has a chance to speak as well. I just had a super quick finger on this discussion. James, I just wanted to mention as a particular example of a duality that I think is interesting and potentially challenging to Penrose's picture is the Sine-Gordon-Thirring model duality. So, there's this, the Sine-Gordon model is based on a real scalar field in 1+1 dimensions, and there's this claimed, in fact, I don't know exactly how rigorously it's been established, but I thought it was pretty rigorously established between that and the Thirring model, which is a fermion in 1+1 dimensions with two components. And so here you have like a pretty explicit example of two models, no gauge invariances, where the number of components is different between the models, but there's still a claimed duality between them. Yeah. And the number of dimensions is very small. So, and also you might also look at the duality between SYK, the SYK duality, and Jakeev-Teitelbaum gravity in 1+1 dimensions. So the SYK model is a one-dimensional spin system with a large number of spins, This is the one that there was all this famous talk about, is there a wormhole or not a wormhole, that was produced. You probably heard about all this. It was about the SYK model, or at least a very truncated version of the SYK model. So the claim duality between that and 1 + 1 dimensional Jakiv tidal-Boyne gravity is potentially also an interesting object of study, where the number of dimensions is different, the degrees of freedom are different, but maybe there's more control over it because it's in lower space-time dimensions. I'm so sorry for taking up that moment, but Noel, please go ahead. We'll have time for one more question from Noel.
Thanks. So I had a question about the very first counting argument, the one that had to do with the worldsheet formulation. I guess the thought is something like, we do lots of calculations in the worldsheet formulation because it's easy, it's in textbooks, a lot of stuff is tractable, but like the more you start digging, it seems like a pretty limited view of what string theory is about. So for example, like you can get glimpses of brane solutions, but you can't really directly describe them without starting to talk about conformal field theories on higher dimensional world volume tubes. So like just naively, I would expect that there'd be more degrees of freedom in a string field theory that has, say, the capabilities of talking about brane excitations.
Yep.
Moreover, if the comparison with ordinary physics involves things like E&M and other gauge theories, like how those sorts of theories might emerge is really complicated and messy, but plausibly might involve brane solutions and things like that. So again, just that like, if part of what might be going on here is the worldsheet view really is extremely limited, at least the way we have it formulated. And both, the emergence of gauge theories and or string field theory are going to involve other sorts of aspects of string theory that just aren't directly described in the worldsheet formulation.
Yeah, I think that's really helpful, and another reason to be a bit skeptical about that first argument. So that particular argument is exclusively focused on the worldsheet formulation, as are much of Penrose's other discussions of string theory. He doesn't talk about string field theory at all, but you might indeed think that that's going to offer you more degrees of freedom and allow you to see like other things emerging and so on. And so that would kind of render moot his first argument. You could also look at like M theory insofar as it exists, and not obvious that those arguments against perturbative string theory and worries about like not enough functional freedom are going to carry over there. I think kind of fairly plausibly they're not. So yeah.
Just to clarify, was specifically the worry about ordinary physics was something like the ordinary physics had more degrees of freedom intuitively than, yeah, okay, that's good.
But he's just looking at kind of degrees of freedom on a worldsheet, comparing it with degrees of freedom of some field set in 4-dimensional space-time, and it comes back to what Nick was saying, like it's really the dimension which trumps, which is going to give you the amount of relative amount of functional freedom. Yeah.
Thanks.
Thanks so much.
I have just one last quick question. And that's how we think about all these problems in when we think in terms of like effective theories, effective field theories. So I don't think any string theorists are claiming that string theory is equivalent to classical GR, or that string theory is equivalent to classical GR plus the standard model. I think the argument that string theorists will generally make is that the universe is far more rich and complex, and there's lots and lots of physics beyond what we can experimentally access, but that we just need sort of the effective low energy physics to look like standard model plus GR. So it doesn't seem to me that what people are even looking for is some kind of agreement and counting of functional freedoms, so much as you need some regime of the claimed theory of everything to look like accessible physics where we can access it, right? I mean, there's this old criticism about string theory that the only real prediction string theory makes is if you built a particle accelerator the size of the Milky Way galaxy and smash things together, you begin to see excited string states. And this is usually presented as like a joke, like we're never going to build anything that big. But that's kind of the point, right? I mean, the string theorists are claiming that if you did that, you would see deviations from physics, but the theory itself predicts that those should be really like hard to detect, right? If you do, reasonably consistent, if you treat GR as like an effective quantum field theory, and you compute, first quantum corrections to things like, Newton's law of gravitation in the solar system, I think that the corrections to Newton's laws are something like 10 to the minus 70 effects. I give students this exercise where you treat the Earth-Sun system as if it's a hydrogen atom, and you compute what's the principal quantum number n of the Earth. And what happens to the Earth's average radius when you go down from one quantum number n to the next, principal quantum number n minus 1, and you discover that the numbers are like 10 to the 150 for the principal quantum number of the Earth, and and the space quantization, right? The radius of the Earth's orbit when you jump from n to n-1 is like 10 to the minus some insanely small number. So when we're making rough predictions about what deviations we expect to see from quantum gravity, they're incredibly tiny. And string theory predicts that stuff will happen there, but just far beyond our experimental access. So I guess the question is, why does Penrose want there to be an equivalence of counting at all if the overwhelming consensus is that quantum gravity, string theory are going to be, much different, but merely only look like three-dimensional physics at accessible scales? I seem to be missing why he wants them to agree at all.
To be fair to him, maybe his worry with the first of these arguments is that the amount of functional freedom for the perturbative world sheet picture seems to be less than the amount.
Yeah.
And
right.
If you're working with string field theory or M theory or whatever it is, you don't have that worry anymore. And I agree with you, as long as it's bigger and you talk about limits and emergence, I'm not worried.
Yeah. Okay. All right. Thanks, everybody. We're going to have to call it quits. I want to thank James again for an incredibly clear and wonderful talk. This was just a spectacularly good talk. I learned a lot. And I'm really grateful that James came and gave the talk. This is now actually our last talk of the spring term, and we're going to be reconvening for talks again in the fall term, so stay tuned for announcements. And I want to thank all of you for being here and participating in this discussion, and many of you for coming to the seminar throughout the academic year. Couldn't do it without all of you. It's nice to see everybody. I hope you have a wonderful summer, and take care. This talk, like all the talks, will be posted to the website and the YouTube channel within the day. So good to see everybody.
Yeah, thank you all for really helpful comments. It was a lot of fun.